Okay, so last time we talked about the two types of calorimetry problems. We said when we're doing calorimetry, we can change change temperature, right? And that's what we did on Wednesday. And what's the formula we use there? Q equals MC delta T, right? And then there's the other kind of calculation when we change phase. What am I talking about there?
State of matter.
State of matter, right? So solid to liquid, liquid to gas, whatever, right? And so there are two types of two calculations we would use there. Get out your handout. Q equals N delta H fusion, and Q equals N delta H vaporization. So this is on your handout here. Heat of fusion is what this stands for. What does N stand for? Number of moles. Delta H of fusion is heat of fusion. Okay, so heat of fusion is what we use when we're melting or freezing. Use for melt, freeze. Okay, over here, N is still number of moles. So if I give you grams, obviously you'd have to convert it to moles first, right? And then delta H vap is called the heat of vaporization. And so you're going to use this one for boiling / condensing. Condensing. Okay? And then Q in all three cases, what does Q stand for? Q equals, it's a word that begins with E. And enthalpy, which is just a fancy word for heat. Okay. So this is what we did on Wednesday. This is what we're doing today. Now the reason why you have to do two different calculations for changing phase versus changing temperature. All right? When you are changing phase, your temperature cannot change. Let me repeat that. If you are changing phase, your temperature cannot change. And the reason why is because during a phase change, all the energy that's going in is going into breaking up the solid into a liquid or the liquid into a gas, okay? So by definition, when you are changing phase, temperature stays constant. So that's why you have to do two separate calculations. So we're gonna make heating curves today. We're gonna combine these together. I'm not going to go over a sample problem of this because I think you can convert grams to moles and multiply it by a value on a handout, right? That's not a hard calculation. What makes this hard is setting up the heating curve or the cooling curve and doing so appropriately. Is everyone okay if I erase this? You okay? Okay. So we're going to make heating curves today that put together what we did Wednesday with what I just mentioned about the vaporization or fusion. So we're going to make heating curves. A heating curve. All right, I'm going to draw a generic heating curve. All right, so let's begin. Draw a heating curve for, let's say, ice at -10 degrees Celsius heated to 28 degrees Celsius. Okay, so this does require us to know some basic information about water. What's the freezing point / melting point of water? 0 degrees Celsius, right? So depending on which way you're going, it's melting or it's freezing, right? We're beginning at -10, so let's draw our axis here. Right, there's 0, right? So -10's right here. And so this is a plot of time versus temperature, okay? We'll do time versus temperature. All right, so at time equals 0, we're at -10, right? And we're gonna put our chunk of ice on a Bunsen burner, and we're just gonna watch what happens. It's gonna be a very boring day, right? Our piece of ice is going to melt. So as time goes on, what's gonna happen to temperature? Go up, go down, stay the same? Well, it's not melting yet, right? It's ice at -10. So then it's gonna become ice at -9, ice at -8, ice at -7, -6, -5, -4, -3, -2, -1. What happens when we get to the, so that's what the first portion looks like. Pretty boring, right? Just watching a piece of ice at -10 go up. Is anything happening to it? Is it melting yet? No. At what temperature does it begin melting?
0.
At 0. Now, if you have a thermometer in there, you'll watch the temperature rising, 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 rising until you hit 0. And then, for that portion of time, you'll physically observe the ice melt. But if you have your thermometer in there, the temperature will not change. Will not change. So during this portion here, right here, we are just heating the ice. So delta T only, right? During this phase right here, what are we doing to the ice? Time's marching on, but what's happening to the temperature? It's staying constant. So what does that mean is occurring? Melting's occurring, right? The ice melts. And so there's no delta T. Because if you are changing phase, you cannot change temperature. Because every single bit of that energy that's going in is going into melting that ice. You can't change the phase and the temperature at the same time. You're either changing one or the other. Once you've melted all your ice, temperature is going to keep rising, right? 0, 1 degree, 2 degree, 3 degree, et cetera, et cetera, et cetera, et cetera, et cetera. Now at 28 degrees Celsius, that's our final temp. This is not to scale. There's our final temp. Is 28 degrees, does that have anything to do with melting or boiling? Is that special for water? No, right? So what's going on during this phase? I mean, during this time period? You're just heating liquid water, right? So there's a delta T only. But are you changing phase? Is 28 anywhere near the boiling point? So if we were going to calculate how much energy is required, we'd have to calculate Q equals N delta H. Now, are we going to use heat of fusion or heat of vaporization? Look at your handout. Which one? Heat of fusion or heat of vaporization? Fusion, right. So that'd be calculation number 1. Now we've got ice melting. So what would the Q calculation be here? Q equals, oh my goodness, I wrote that in the wrong spot. Sorry. Delta T only. This is Q equals MC delta T, where we're going to use the C of ice, right? I was ahead of myself. This is where we're going to use delta H of fusion, right? We're melting here. Here we're just changing the temperature of some ice, right? I screwed up. My kids become super perfectionists right now. Like they're way into like, I can't make mistakes. So I try to let them see me make mistakes. So here you go. Here's an example of me making a mistake. This one's for you, boys. All right? If you are changing the temperature only, you cannot be changing phase. That's why we split these up, right? MC delta T using the heat capacity of ice. Because from -10 to 0, it's just the chunk of ice, right? Using the heat capacity of ice, you're just increasing its temperature until you hit the magic number of 0 and you're melting the ice, right? Once you hit 0, all the energy that you're throwing at that chunk of ice is going into melting it. That's why we're using N delta H of fusion. Make sense? Now we've got all of our ice melted. We're liquid water at 0 degrees Celsius, and we're going to increase the temperature. How would we calculate Q here?
MC delta T, where C is the
Right, good job. C of liquid. We're going to use Q equals MC delta T. And then to get the total of the total Q total is just Q1, right? Because there's calculation number 1, here's calculation number 2, here's calculation number 3. So Q1 plus Q2 plus Q3. Now there is something really important you need to watch. Watch, 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 watch. Can't emphasize this enough. When you do Q equals MC delta T, your unit is going to come out to be what? Your unit is going to be what? Q is going to be in, look at your handout. Heat capacities are all joules per gram degree Celsius. Joules per gram degree. Grams and degrees Celsius are going to cancel each other out, right? So what's the unit of Q going to be? Joules. So unit here is going to be joules. Unit here is going to be joules. But look at heat of fusion. Heat of fusion is kilojoules per mole. When you multiply kilojoules per mole times moles, the moles cancels out. So what's your unit here going to be? Kilojoules. Can you add joules to kilojoules? No. So you either need to convert kilojoules to joules or these two joules to kilojoules. I prefer to convert everything to kilojoules because I like small numbers, but that's just me. It's not wrong to call it 1 times 10 to the 4th or 1,000, right? So just, you pick which one you want, or 1 times 10 to the 3rd, I should say, right? You pick one, but be consistent. Make sure your units match. Matching units. Okay, your units have to match before you add. Because if you try to add joules and kilojoules, you're going to get a mess. So, we're going to do some heating curves and calculations for heating curves today. That's all we're doing. Okay? This is the second half of calorimetry. And then we'll do a cooling curve. A cooling curve is exactly the same as a heating curve, it just is going the other direction. So let's do an example. Let's start on the screen. Let's start here. Calculate the heat required to heat 50 grams ice at -5 degrees Celsius to liquid water at 25 degrees Celsius. So we're going from -5 to essentially room temperature. I'll give you a second to jot that down. Now, drawing a heating curve is not only something I'm going to require of you, but it's also a useful thing to do because it helps you stay organized. If you draw that heating curve, it will spell out what steps to do when. So not only am I going to make you do it, I'm going to make you do it because it's a good thing to do, right? It will help you stay on track. You will less likely to make a silly mistake if you draw the heating curve. So that's part of the reason too. I'm going to make you do it so that you can show me that you know what you're doing, but also so it'll help with your calculations. So let's draw our heating curve first. All right, so we are dealing with ice. Freezing point / melting point 0, right? That's our magic number. But we're not beginning at 0, we're beginning at -5. All right, this is time, this is temperature. All right, so at time equals 0, when we begin, the temperature is -5. As time marches on, the temperature of that chunk of ice is going to increase until I hit this magic number. So what's happening here? We're increasing the temperature of ice, right? So we're doing Q equals MC delta T or N times some heat of something. MC delta T. And which C do we need to use? C for ice. So that's calculation number 1. Now, when we hit 0, what's our curve going to look like? Is it going to be diagonal or is it going to get flat? It'll be flat. Why?
Because it has to melt.
It has to melt. And all the energy at that point during melting goes into melting and nothing else. So during this time, we're going to do Q equals N delta H. Fusion or vaporization? Fusion. And so this is calculation number 2. And then what we just did a minute ago, we're ending at 25. There's nothing special about 25 degrees Celsius other than it's room temperature in most calculations. So Q equals MC delta T. We're using the heat capacity of liquid. So that's calculation number 3. All right, so let's go through and let's do all our calculations. I've still got room on the frame here. So calculation number 1, Q equals MC delta T. So the mass is 50 grams times the heat capacity of ice. What's that? Look at your handout. Heat capacity of ice is 2.03 joules per gram degrees Celsius. And what's delta T here? How do we calculate delta T again? Delta T is always what minus what? Final minus initial, right. So my final is 0, my initial is -5. So 0 minus a -5 gives me +5, right. So delta T is 5 degrees Celsius. So degrees Celsius cancels, grams cancels, my unit's gonna be in joules. So we break out our calculator. 50 times 2.03 times 5. We're going to carry out our decimal places and round at the very end. So 507, and my unit is joules. Do we agree on that value? Those of you calculating along with me? All right, let's do number 2. Calculation number 2. Q equals N delta H fusion. Well, N is number of moles, right? Am I given moles? No, so what do I need to do? Convert grams to moles, right? 50 grams, molar mass of waters, 18.01 grams per mole. So grams cancel. I'm in moles. Can I take that number and now directly multiply it by heat of fusion?
Yes.
Yes, I can. So the heat of fusion is, on my handout, 6.01 kilojoules per mole. Moles cancels, I'm left with kilojoules. So 50 times 6.01 divided by 18.01 gives me 16.7 kilojoules. Do we agree on step 2's number, how it was obtained? All right, now in step 3, Q equals MC delta T. So the mass is still 50, that hasn't changed. So 50 grams. Heat capacity of liquid water, is that the same as ice? No, what's it for water? Liquid. 4.184 joules per gram degrees Celsius. And now what's delta T? It's calculated as final minus initial. So 25 minus 0 gives me 25, right? So degrees Celsius goes away, grams go away. Now I'll just punch it into my calculator. 50 times 4.184 times 25 gives me 5,230 joules. Now, do we want to keep everything in joules or do we want to keep in kilojoules? Makes no difference to me.
Kilo.
I like kilojoules too, smaller numbers. So if we divide by 1,000, move the decimal 3 to the left, that'll be 0.5075 kilojoules. That's already in kilojoules. And this would be 5.230 kilojoules. Now when I add those up, am I still on the screen? Oh, just barely. 0.5075 plus 16.7 plus 5.23 gives me 22.43. For the sake of argument, because I don't like having just one sig fig. Let's pretend that this was at -5.0. So we can keep 2 sig figs. That's the beauty of making up your own problem, right? Kilojoules. You can change it if you don't like it. Did I stay in the screen? Oh, yes, just barely. Do we see how we did that one?
Simple arithmetic.
That's all it is. Just setting up the heating curve is the hardest part. That's the hardest part, right? If you set this up, it's a roadmap to the calculations. Because if you can do this, it's very visual, right? This should tell you, hey, this is what I need to do here, this is what I need to do here, this is what I need to do here. So if you can get past this part, then the arithmetic shouldn't be too awful, I hope. I'm going to give you something slightly different, and I'm going to see if you can do this one. I'm going to let you try it, and then I'll go over it. Is everyone okay for me to erase? Yes. The recording will be posted today, so if you missed something, you can go back and look at the recording. And if you like PowerPoint instead, last year's version I did entirely PowerPoint instead of writing it out. I've just decided I don't want to do PowerPoint anymore. So I'm going to do everything on the board. So if you like PowerPoint, you can go look at last year's. Got a belly up here. It's kind of fun. All right, you try this one. How much heat is required to increase the temp of, let's do 90.5 grams liquid H2O at an initial temp, let's just do room temperature. To 115 degrees Celsius. So make your heating curve, set up your calculations, take it away. I'm going to pause the recording while you do that. Okay, even if you're not all the way finished, let's go over this one so we have enough time to get through cooling curves as well. So now we're at a different starting point, right? In the previous two, we were below zero, right? So we had to freeze, we had to melt. Do we have to do any melting in this one? No, we don't. So let's make our heating curve. We're beginning, we don't even need to draw this axis unless you're going to draw it for fun, right? Because we're not below zero. We're starting at 25, right? So when t equals 0, we're at 25. We're going to increase. What's the magic number that we were looking for here? 100. What's special about 100?
It's more of vaporization.
That's the vaporization point, right? So what happens when we hit 100?
Plus lines.
It's going to get flat. And during that point, what process is occurring? Vaporization, which we affectionately refer to as boiling, right? So we've got calculation number 1, calculation number 2, and then after we melt and after we vaporize all the water, then what happens? We're just increasing the temperature of the steam, right? 115. So Q equals MC delta T using the C of what? Liquid water. Here, Q equals N delta H what? Vaporization this time, right? And then calculation number 3, Q equals MC delta T using the C of
liquid
steam. Right. So remember, water has 3 different heat capacities because one's for ice, one's for liquid water, and one's for steam. Those heat capacities factor in the differing intermolecular forces for those states of matter. All right, so let's do our calculations. I'm still right here. Q equals MC delta T. And so this is for the liquid phase. So the mass is 90.5 grams times the heat capacity of liquid water is what? 4.184 joules per gram degrees Celsius. Now what's delta T? Delta T is always final minus initial. So final minus initial. So what's that? 75. So 75 degrees Celsius. Degrees Celsius cancel, grams cancel. So my unit's going to come out to be joules. So 90.5 times 4.184 times 75 gives me a really big number. We'll round at the end. So 2839 8.9 is what my calculator says. My unit there is joules. Agree on step 1? All right, let's do step 2. Now we're going to vaporize that water. So Q equals N delta H vaporization. So what do I have to do before I can multiply by heat of vaporization? Got to convert it to moles, right? So 90.5 grams times 18.01 grams per mole. Now we're in moles. Now we can multiply by heat of vaporization. Heat of vaporization, according to my handout, is 40.67. Why is the heat of vaporization so much bigger than the heat of fusion? Which state of matter has more energy associated with it, a gas or a liquid? A gas. Think about why a gas has so much energy in it. Because you've got to put so much energy into it to get it to that point. Okay? So that's quantitatively explaining why gases have so much energy. 40.67 kilojoules per mole. So moles cancel. All right, now we've got 90.5 times 40.67 divided by 18.01 gives me 204.4 kilojoules. We agree on step 2? All right, now let's do step 3 using the heat capacity of steam. Q equals MC delta T. So 90.5 grams times, what's the heat capacity of steam? 1.84. This is joules per gram degree Celsius. Grams cancels. And now what's delta T? It's always final minus initial. So 115 minus 100 is what? 15 degrees Celsius. So degrees Celsius cancel gives me unit of joules, 90.5 times 1.84 times 15 gives me 2497.8 joules. Now again, you can leave everything in joules. There's nothing wrong with that. You're just going to get a big honking number with a bunch of zeros. So let's convert everything kilojoules. So if you move the decimal 3, 1, 2, 3, right? That's 2.498 kilojoules. That one's already in kilojoules. And then 1, 2, 3 gives me 28 point, let's just round that to 28.4 kilojoules. Because I'm only going to be able to keep 2 sig figs anyway. So 28.4 plus 204.4 plus 2.498 gives me 235.2, which we then round to 2 significant figures would be what? 235.2 rounded to 2 sig figs would be 240, no decimal place, right? My unit would be kilojoules. Do we agree on this one?
Yes.
Any questions on how this one works? Now a cooling curve is going to work exactly the same as a heating curve, except now you're starting here and you're going down the stairs. Actually, you're going down the stairs this direction. And there's one slight difference. Is everyone okay if I erase? Again, if you missed something, the recording will be posted later today. There is one difference in our calculations. And once I explain it to you, you'll see why it is the way it is. When we are doing a cooling curve, heating curve is heat going in. Right? We have a positive value of Q. All of our answers so far have been positive, right? A cooling curve is what?
Heat leaving this.
Right. Equals heat going or exiting system. So what's Q going to be here? Negative Q. So when you're doing a cooling curve, make sure that you, for your Q equals MC delta T calculations, no change needed. It's going to come out negative already by default. Because think about it. If you're cooling down from 120 down to 100, right? Delta T is going to be T final minus T initial. So that's 100 minus 120. That's negative 20. So your Q is going to come out to be negative because you've already got a negative as part of the equation. Does everyone see? Because if you've got a negative delta T, that's positive, your answer is going to be negative. Right? So no change is necessary if you're doing Q equals MC delta T. But when you're doing Q equals N heat of fusion or Q equals N heat of vaporization, you have to change the sign okay, to reflect heat leaving. Right? Exothermic, heat is leaving. Because heat of fusion is the same thing as enthalpy of fusion, that's heat. So if this is heat that I am removing, you need to change this sign to negative if you are cooling down. Okay, because that's heat you have to extract. Here, you don't need to change anything because your delta T factor is going to come out to be negative, so nothing needed on your part. But if you're doing heat of fusion or heat of vaporization, like so right here, right, this would be Q equals N delta H vap, you would need to put a negative sign there. Okay, take the negative of it. Does everyone see why we changed that sign? Yes, because that's heat that you have to take out of the system. All right, so let's do a calculation or two. I'll do one, then you do one. All right, so how much heat is removed when 15 grams steam at 130 degrees Celsius cools to 85 degrees Celsius. How much heat is removed when 15 grams of steam at 130 degrees Celsius cools to 85 degrees Celsius? All right, so let's make our cooling curve. We're beginning at 130. So when T equals 0, we've got steam at 130 degrees Celsius, right? And as time goes on, what's going to happen to this temperature? Is it going to go down or go up? It's dropping, 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 dropping until I hit what value? 100. Okay, so during this is our first calculation. What are we doing? Q equals MC delta T or Q equals one of the heats? MC delta T, right. And which heat capacity are we using? C of steam. Good. Now we're at 100. What's going to occur? Time's going to continue, but what's going to happen to the temperature? It's going to stay constant, right? Because can you change temperature during condensation? Because that's what's occurring, right? Gas to liquid is condensation. So can we change temperature during that phase change? No. So calculation number 2, Q equals N times delta H of vaporization or delta H of fusion? Vaporization. And then what do we need to do to represent that fact that this is cooling? What do we need to do? Change it to negative, right? And now we're all condensed in the liquid phase and we're lowering the temperature to 85. That's my final temperature. This is way not to scale, but who cares? What's our third calculation? Q equals MC delta T. And which C are we using now? The liquid phase. Okay. So let's do our arithmetic. Number 1, Q equals MC delta T. So that's 15 grams times the heat capacity of steam. And my handout says 1.84 joules per gram degrees Celsius. And delta T is always final minus initial. So 130 minus 100 gives me, final minus initial. 100 minus 130, because remember this is the final, this is the initial. T final minus T initial. So 100 minus 130 is negative 30, right? So negative 30 degrees Celsius. Degrees Celsius cancel, grams cancel. So when I do my math, 15 times 1.84 times 30, take the negative of that, I get negative 828 joules. Okay. Do we agree? All right, calculation number 2. Q equals negative N delta H vaporization. So we have to say, okay, I've got to convert grams to moles. 15 grams times 18.01 grams per mole. Grams cancel, now I'm in moles, times the heat of vaporization. I just pulled the negative out and put it here at the front because I don't like having a negative in the middle of an equation because that's just me. But if you wanted to keep it right there, be my guest, right? You're just taking a negative of the whole thing, in other words. So heat of vaporization is what? 40.67. So 15 times 40.67 divided by 18.01. 33.9 kilojoules, just rounding to one decimal place. And then lastly, Q equals MC delta T. So 15 grams times heat capacity of liquid water, this time, 4.184 joules per gram degrees Celsius. Delta T is final minus initial. So what's that? Negative 15, right? That's why you don't have to change the sign here. So negative 15 degrees Celsius. Degrees Celsius cancels, grams cancel. So 15 times 4.184 times negative 15 gives me negative 941.4 joules. Still on the screen? Okay, barely. So all right over here. So Q total. Do you want to keep everything in joules or do you want to convert to kilojoules? Kilojoules. Okay, so this in kilojoules would be negative 0.828 kilojoules, right? Plus, this one's already in kilojoules, 33.9 kilojoules, plus, convert this one to kilojoules, move it 3 over. Let's see, that one, oh, We lost our negative there. It's like, wait, something's wrong. Negative 0.941. Because I forgot to write the negative sign there. Because I'm writing it down here going, wait, what happened to my negative? I just forgot to move it up there. So my final answer, when I round to 2 sig figs, 0.828 plus 33.9 plus 0.9414. My final answer is negative. I can only keep 2 sig figs. Negative 35.67, which we've rounded to negative 36 kilojoules. That's the amount of energy that has to be removed, right? Is it okay to have a negative Q? Yes, that means that's energy that you are taking out of the system. Make sense? You ready to try one involving a cooling curve? Okay. Are you all right for me to erase the board? Everyone okay to erase the board? Okay. All right, last problem. I'm going to pause the video after I write it out so that you can try it. What is the change in enthalpy when 45 grams steam at 125 degrees Celsius is cooled to -8 degrees Celsius? Pause the recording, let you try that one. Probably, you may not be finished yet, but we need to get started so we can finish this problem before class ends. So let's start our cooling curve. This is as bad as it's going to get, right? This is like the worst case scenario because you've got to go from steam at some temperature to ice at some temperature below 0, right? So this is like the worst you could have. If you can manage this one or the heating curve version of it, then you can handle any of them. So we're starting at 125 degrees Celsius. Am I on the screen still? 125 degrees Celsius. We're going to, as time goes on, we're going to cool until we hit 100 degrees Celsius, right? So that's calculation number 1. Q equals MC delta T using the C of steam. Then what's going to happen, we're going to condense. I move my axis down. Give myself that room here. Axis down. We're going to cool, right? So condensation's occurring here. So Q equals negative N delta H vap, right? Because that's vaporization in reverse. So we've condensed all of that steam to liquid water. Now we're going to cool. Right, that's a bigger area. Okay, so here we're doing Q equals MC delta T, right, using the C of liquid. Then we're going to freeze when we hit 0, right, because that's the freezing point. So calculation number 4, Q equals negative N delta H of fusion, right? And now we've got to cool it down to -8. So Q equals MC delta T using the C of ice. So that's calculation number 5. And then we add them all up. Do we agree? All right, I'm going to erase my heating curve, my cooling curve, because it's taking up whole board here. So calculation number 1, I'm going to have enough room to write 5 calculations. I got to have some space. Number 1, Q equals MC delta T. So 45 grams times the C of steam is 1.84 joules per gram degrees Celsius. Delta T, we went from 125 to 100, so final minus initial, so what's delta T? Negative 25 degrees Celsius. I'm going to just write everything on the board, and then I'll do the arithmetic all at once. 2, Q is equal to negative N delta H vaporization. So negative, and now we've got 45 grams times 18.01 grams per mole. So grams cancel, times 40.67, right? Yes. 40.67 kilojoules per mole. So we'll do all our calculations at once. Then for calculation number 3, Q equals MC delta T. So that's 45 grams times heat capacity of liquid water, 4.184 joules per gram degrees Celsius. So grams cancels. My delta T here is what? We're going from 100 to 0. So what's 0 minus 100? Negative 100. So we'll see what that gives us. Calculation number 4 is Q equals negative N delta H of fusion. So that's negative 45 grams times 18.01 grams per mole times heat of fusion is 6.01 kilojoules per mole. So moles cancels, grams cancels. Let's see what that gives us. And then calculation number 5, Q equals MC delta T. So that's 45 grams times heat capacity of ice is 2.03 joules per gram degrees Celsius. And now my delta T is negative 8 minus 0. Oops. So times negative 8 degrees Celsius. All right. So let's do our math. 45 times 1.84 times 25, negative, of course, 2070 joules. So that will be negative 2.07 kilojoules. 45 times 40.67 divided by 18.01. Negative 101.6 kilojoules. 45 times 4.184 times 100. Negative, of course, would be negative 18828 joules. Move the decimal 3, 1, 2, 3. So negative 18.8 kilojoules. 45 times 6.01 divided by 18.01. So that's negative 15 kilojoules. And then 45 times 8 times 2.03. That gives me negative 730.8 joules, so negative 0.731 kilojoules. Do we agree on all those values? So Q total 2.07 plus 101.6 plus 18.8 plus 15 plus 0.731 negative, and I can only keep one sig fig. Oh, for the sake of argument, let's just make it 8.0. I don't like doing one sig fig kind of problems. At least do 2. So my calculator spits out negative 138.2, which we were around 2 sig figs, negative 140, no decimal place, and my unit would be kilojoules. Do we agree? All right, that's where we're going to stop for today. Have a good weekend, and I'll see you Monday.